Okay, let's get going. Thanks everyone for joining. It's my pleasure to introduce Andre Ferreira, who's a data scientist at TransitionZero. I've also had the pleasure of working with Andre, so it's really delightful to welcome him to the stage here. Andre is a data scientist at TransitionZero, which is a non-profit in London, which applies data science to find leverage for decarbonisation. He's previously worked at Jungle doing predictive maintenance for wind turbines. So he's got a varied experience in climate tech. And today, he'll be talking about how TransitionZero build data pipelines to allow them to model the emissions and profitability of coal power plants, and thus construct very strong economic arguments for not building new ones. Thanks very much, Andre.
Right, hi everyone, and thanks Archie for the introduction and for having me in the conference. So yeah, you know, in a conference, it's important to have a fancy title. So I've named this presentation to be a data-centric approach to modeling CO2 emissions from power plants. Let's get into it. So who am I and why should you care about this? Well, caring about data, I think it's important, and it's not only me saying it. So for example, Andrew Ng, who started things like Google Brain Research and does a lot of popular courses on deep learning, he says that the model and the code for many applications are a solved problem, and now we really need to make the data work. And yeah, I think this is important because beyond the computation power, you see that data quantity and quality is actually a big differentiating factor. And especially in critical domains, it's really important to have a deeper understanding of the underlying data. So in terms of who we are TransitionZero, a climate analytics nonprofit, and we use tools such as data science, financial modeling, and open data so that we can bring about actionable analysis. So for example, we have this project that we released recently of coal to clean price switch. So you can kind of compare how cheaper it is to switch from coal to clean energy instead of to gas. And we also are a founding member of Climate TRACE, a coalition of multiple organizations where we want to track greenhouse gas emissions from multiple sectors of society. And we do this mostly through satellite data and machine learning. So I'm going to talk about some of these main steps of data iteration. So it's going to be about building, improving, monitoring, and researching. Let's start with the building part, of building the models and the data. So in my view, some of the main steps for this involve first understanding the problem. So really, you know, do a literature review, benchmark what are possible solutions, define your requirements, and then you can actually go about and collect some data and build your initial data sets. You can then explore the data from visualizing it to doing very important steps like actually mimicking the machine learning environment. We'll see how. And then you can develop minimal viable projects. That is, from all things such as defining your minimum requirements and then actually iterating through some fast and simple experiments. So let's go through a simple use case of understanding the data. Let's start with looking at this Ninghai power station from China. And what we see here is that we have a flue stack, which is this tall, narrow tower from which the combustion gases come out of. And then you have this cooling tower, this wider structure where hot water vapor comes out of. And that is the result of water cooling processes of the power plant. What you'll see is that while the power plant is in operation, you'll see all these plumes coming out of potentially both structures at the same time. And the characteristics of those plumes, such as their size, number, and other patterns, will be related to the power plant's utilization and in the end, its emissions. You can also see the power plants from space, as you can see here in this satellite imagery from the exact same power plant. And you can see the two flue stacks that it has, and also these big wide gaps, which are the cooling towers. Then in certain satellite imagery, you'll be able to see that there are plumes coming out of all of these. And this is, again, what our models will be looking after. How do we actually download all this satellite imagery? Well, we use a combination of 3 satellites, for which we use Google Earth Engine to process and download Landsat 8 and Sentinel-2 imagery. And then we have this higher resolution PlanetScope imagery, which has its own advantages. So let's compare all these sources, right? So we have this Landsat 8, which, as you can see, might be a bit more blurry. It also has kind of a slower revisit rate. That means we only have a new image of the same site around every 16 days. And it's blurry because essentially each pixel is at least 15 meters on the ground. But then it has the benefits that beyond the visible light that we see in this imagery, we also have things such as shortwave infrared and thermal bands, which can be very useful to detecting heat. Then we have Sentinel-2, which, as you see, is an upgrade on that spatial resolution, and it also has a higher revisit rate of every 5 days, although we kind of lose the thermal bands. And then PlanetScope, even though it only has this near infrared bands, it does revisit every single day, basically, and it has a very nice spatial resolution of 3.7 meters. But this goes beyond imagery, and so we also have metadata for the power plants. For example, we use Global Energy Monitor's datasets to assess things such as the location and capacity of the power plant. And then we also use OpenStreetMaps, which is kind of comparable to a Wikipedia of maps, in that it's a community-driven annotations of mapping things such as power plants. We also have ground truth, which in our case corresponds to power generation data of power plants. And we have it for Europe, the US, and Australia from their respective energy companies in a way. And so in the part about really exploring this data, we do a lot of hand labeling. So an example of this you can see in this image. So for example, here we're annotating for each sample whether we think the power plant is off or on, and we can also detect things such as where are the plumes coming from, if it's cloudy, or if it has any other weirdness in the image. And so this kind of allows us to really assess human performance, and it can serve as a kind of a benchmark for our models and really assess the feasibility of what we're trying to do. And so, for example, in some cases, we got around 90% accuracy in doing our own human labels of the samples. So this kind of tells us what we expect the models to perform like. And it can also help us identify things such as outliers and other limitations of our approach. In case you're curious, we use this open source framework of Pigeon XD for this kind of annotations. So going on to the MVP, how we integrate all this data is that we have this metadata, as we were talking about things like the name and coordinates of the power plant, as well as its technologies. We then have the power generation ground truth, and we have satellite imagery from those 3 satellites I mentioned. So what we do is we aggregate this metadata and ground truth into Postgres databases, where they'll have fixed schemas and get frequent updates. We then also save our satellite imagery in object storage, as well as some feature files. And then we combine all of this into a data warehouse, in this case, BigQuery, where we can actually do things such as take snapshots of all the data, and also do some quick experimentation and analysis. So what was our initial approach to this? Well, we had training data, as we saw, for Europe, US, and Australia. So we would train our models on data from those regions and then apply inference to basically the rest of the world. And the models we initially tried were things such as gradient boosted trees and convolutional neural networks. And this would be applied directly onto one single large image from the satellites. And we would do basically an on-off classification here of detecting if a power plant is off or on. And yeah, that was the initial approach. And to be honest, the initial metrics weren't super great. So we were getting something like 0.7 mean average precision, which is worse than what we were expecting from the hand labeling. So let's see how we can improve stuff. So some of the main steps for this stage, I would think, is doing things such as consulting the domain experts. This is very important to actually have a better understanding of the failure modes of the models and identify how to improve it. Then we have the part of actually reassessing what we know now and trying to find out what are the limitations of new approaches. We can then gather new data through annotators and new data sources, and then release new versions of the data and retrain the models. So let's see an example of how we improved. So we started out by this problem identified by our experts, which was that plumes originate from different structures of the power plant with different characteristics. And we should actually, pay attention to the differences in things like the fuel type and the cooling technology of the power plant. So what we explored here was modeling not just on one large image of the entire power plant, but actually model on multiple individual smaller patches on the plume sources. And then also create a separate model for each type of plume sources, actually. So the outcomes of this is that we really improved all of the models, and in particular, models on coal and DT performed with over 0.95 mean average precision, which is already much better than the 0.7 we had before. This also allowed us to start training new types of models, such as regression models to actually predict the power generation, and some time series models to actually aggregate this all into a time series. So for example, we can see here that through OSM, we can actually label each individual infrastructure of a power plant. And then we see here the new models that we have where they look into multiple patches. In the case of CNNs, we have an attention layer, and then we can do power generation regression beyond the classification problem. We also had this interesting aspect of some flue stacks, some chimneys of power plants have an FGD technology where their plumes are actually bigger than usual. So our domain experts suggested modeling those types of flue stacks. So we started annotating them and training models specifically for them, which led to greatly expanding the coverage of power plants we could model by around 626 terawatts, or 91% of our previous data set. And we got some pretty good models for this type of technology with up to 0.9 mean average precision. So we have an example here that is interesting to see. So we have this very faint plume from a flue stack that doesn't have FGD technology. And then we have these two, which have FGD technology and have very visible plumes. So we do have some edge cases and limitations that were identified over time. So for example, weather conditions can have a big impact in our models, both because they can obscure the view of the power plant and because they can actually look like plumes and also interfere with the signal we see. We also have some interesting cases of power plants that use things such as district heating, where they transfer part of the heat onto other buildings and not necessarily onto plumes. And we also have more efficient uses of water that make it harder to see a plume. And then one of my personal favorites is this edge case of a power ship. So this is essentially a fossil fuel power plant on a boat. So we can't really rely on a single fixed coordinates because they can be all around the world. To be honest, I think it would be even more fascinating if one day we would have renewable power ships, but that's a conversation for another day. Well, how do we actually gather new data then? We do use annotators so that they can annotate new patches of power plants for us. They can also compare our multiple data sources and then validate the characteristics of each power plant. For example, we have set up a notebook for the annotators to look through the maps and validate what kind of imagery we're getting. And then they can use this spreadsheet to validate each individual power plant. Going on to the part of releasing, I think it is very important, the versioning process in machine learning, because while in traditional software, we would mostly just version the code, we also need to pay attention to versioning the data, which in our case includes both images, features, and all these metadata and ground truth tabular data. And also versioning the models themselves after they're trained and potentially assigned to production. This allows us to have more reproducible pipelines and also get a better hold of the experiments we do and then go on to monitoring, which I'll talk about in a second. But so before we get to that, just so you have an idea of the kind of data pipelines we do this Airflow pipeline for each data release, where we initially get all the attributes and patches for all the power plants. We then do this distributed computing so that we can kind of manage all of this in a more efficient way, where we first apply filters to filter out things like very cloudy images. We then generate the tabular features that will be used by some of our models and save them in Google Cloud Storage. We can also generate TF records, which is a special kind of data format, which is mostly for the images and our CNN models. We can then finally run our image models that will be run on each individual sample, doing the on-off classification and power regression, and also run on the top of it the time series models to get the time series of emissions and power generation. This is all done mostly through the Google Cloud ecosystem, and we also do some Grafana dashboards to keep track of all of this. Speaking of keeping track of things, let's go to monitoring. So some of the main steps in this is that we first need to track what can be changing between different runs of the data pipeline. We can do things such as detect data drift and communicate what is highlighted there. We can then validate the data and the models. This can be very crucial to detect some potentially silent problems and check if there's any breaking problems there. And then having all of this, we can actually adapt our strategies, such as correcting some samples and doing modeling approaches such as balancing the sample weighting. So let's go back to our pipeline. We now have this step of summarizing the data release. This is essentially a step of creating these tables to get a bigger picture of our data. And we save these summaries in separate tables in BigQuery. And they can help us get a sense of a lot of things, such as how many images are passing through the filters, as we see here, or have a sense of the distribution of classification from our models. Having these summaries, we can run the data validation. And as we were talking, this can be very important because there's a lot of nuance in both the input and output data that we generate. So it's important to check its quality. And having this automated helps really to sense check the data and identify problems that might be breaking our models without us realizing it. So we developed this framework to assess data based on expectations, built on top of these data releases that we've been talking about. And they can operate both on the summary tables and a lot of other data, such as model performance. So what we see here is that we can create these visualizations of the different types of expectations or data tests that we have, also ordered by their priorities and with ownership of those expectations. And we can also see in BigQuery the examples where those expectations weren't met. So we can quickly debug our models and data. We also have these other dashboards to see things such as the time series of the outputs we have for each individual power plant. So combining these dashboards with the data validation, we can identify issues such as missing images. So we have this large power plant, for example, that was missing a lot of images for some satellites. We can identify patches that have the wrong geolocation. So for example, a patch has coordinates much further away from the actual center of the power plant, and the model will just be running on all NANDs, essentially, thus the flat time series. And we also, interestingly, have regions of the world that are much cloudier than others. And so we can also see that we might have less data points for those regions. Having done this data validation step, we can notify the recap of that validation. So because, having the dashboards and tables, they are good, but they require some proactive examination and actually going and analyzing what's happening, while having some kind of notification, such as the Slack bot that we defined, can actually, actively and automatically let us know what's going on with the data and point us out through where we should be looking at and who's responsible for what. Let's go on to our final step of researching through new data. So the main steps here, I think, are discussing with the experts and literature what could be new kinds of data that would facilitate improvements. Knowing that we can experiment with new internal annotations, for example, and do things such as a new hand labeling study to kind of assess that new approach. And then we should always keep an eye, of course, in new data sources, both from our current providers and influential people in the domain, so that we can try out new modeling approaches. So, for example, in our use case, we see some potential avenues of research. So there's a lot of satellite providers working on higher resolution thermal imagery, such as Satellite View and NASA themselves. This could allow us to model more directly the power generation in terms of heat. Then we also have some interesting types of power plants where they have large volumes of water outputs. If we can clearly assign these to the power plant generation, we can also use that as another signal for our models. And then there's this exciting work of some satellites that are being launched to actually try to directly capture CO2 emissions. And so, of course, this would also make things much more straightforward. So, wrapping things up, let's go to some of the main takeaways. Well, I think it's clear that data collection, aggregation, and its own exploration are crucial bits of any machine learning project. We also see that domain experts and hand labeling are very important for iterating on the models. And data versioning can allow us to have reproducible experiments and lead us to the monitoring tools that we can use to actually validate our results and quickly identify problems before they become too problematic. As a quick shout out, I'd just like to show some examples of how TransitionZero uses data. So for example, we've done projects such as the Turning the Supertanker report, which Al Gore has actually passed on to John Kerry and Chinese delegates, and could have had some impact on anticipating closure of some coal power plants. And we have this very recent new open data project, the Coal to Clean Carbon Price Index, where we actually track on a frequent basis what are the costs of switching from existing coal power plants to clean energy instead of gas, of course. Yeah, so I think that's mostly it on my side. You have my contacts here, and I'm open to any questions.
Thanks, Andre. That was an awesome tour from start to finish of a successfully implemented machine learning project. And I love the focus on data, as you say, often neglected, but typically the hero and the difference between a successful project and an unsuccessful one.
Yeah, sure.
We have one question already, which has flowed in from my colleague Vlad. And he asks, how do you version your data? And did you have any problems coming up with a scheme for that? Did that always work well?
Yeah, so I'm aware that TransitionZero tried some other strategies before. There's, for example, this framework of DVC, but it seems to have a bit of a learning curve, and we faced some issues with that before. So our current approach really is somewhat simple. We basically have this frequently updated underlying data from Postgres and all this satellite imagery that we keep on downloading. What we do is that every so often we snapshot all of it, so that we have like a timestamp, like a frozen version in that timestamp of all of the data, or at least all of the data that will be important for our models and analysis.
Perfect. And then whenever you are training a model, there's some reference somewhere to what the timestamp was of the data that it was using.
Yeah, exactly. Each data release is labeled, so every model kind of targets a specific data release.
Beautiful. Great. We've got another question from Ornella, who asks, how are the on-off classification and the power plant emissions predictions used? Like, I guess, what is the link between that work and the work you talked about at the very end there, making these reports?
Yeah, that's a good question. Well, first of all, for example, for climate trace, as I was talking about, we can associate the onness or the power generation of power plants with their emissions through emission factors. And so that can lead us to things like having this public data set of emissions on a global scale without relying too much on kind of self-reported emissions. And then on the side of TransitionZero, yeah.
So could you just dig into that emission factor topic a little bit? Because I think for some people in the audience that won't be so familiar.
Yeah, emissions factors is essentially things like you associate how much, basically how much emissions you usually get from things like coal or gas or oil. This has a lot of complexity behind it, but yeah, it's essentially how do you translate the power generation from a power plant, given the fuels it uses, onto the actual emissions.
Right, so you're measuring the activity of the power plant, and then you're going to multiply through by a number which converts that activity into CO2.
Exactly, yeah.
Perfect.
And so, to give another quick example is just that on TransitionZero, for example, we do then get these power generation and emissions data and integrate it into our financial models, which are essentially things like, detecting that in China, a lot of the coal power plants are running at very low capacity all the time. So that leads us to kind of this kind of analysis that, they're actually running at a loss. So it would actually be a savings to replace the coal power plants with clean energy.
So when you say low capacity, you mean that it's not on all the time?
It might be on sometimes, but even when it is on, it's not running at its fullest. So, you have this problem that, of course, a power plant will always be the most useful if it's being run to the max, essentially. Mm-hmm. And if it's being just underused, you just have like an unused asset in your hands, which is just giving you costs.
And so you mentioned two kinds of models, one the on-off classification and the other the regression. I guess, does the regression model allow you to tell whether a power plant is fully on or half on?
Yeah, so basically that's one thing that we do is that trying to distinguish the levels of onness that a plant is, or the power generation that it's outputting. And we've been detecting that things like the plume size or the number of units that are actually having plumes can be correlated with this generation.
Awesome. Another question from Adil, who asks, have you tried active learning? So their summary is updating an existing model with new annotations as opposed to training from scratch. If so, have you had any luck with that?
That's a good question. We haven't actually tried that. We've been sticking mostly with just training our models based on what we have from our ground truth data. So essentially, we have this high fidelity data of power generation coming from the US, Europe, and Australia. And we rely on that to actually train our models. It is important here as well because perhaps active learning might be very useful, especially in classification problems. But in this case, we do also want to very precisely try to model power generation. So yeah, it's important just perhaps for now do with our approach.
And one from me just on that topic. So you've got good ground truth data for a subset of geographies. How do you see the generalization across geographies working? Do you have any insight on that?
So we have data analysts that go through our outputs. And we also use things like the data validation tools that I mentioned to try to check how the outputs vary between regions. It is interesting. Of course, there are some regions of the world that might introduce some problems, because of course the model will always have bias on what it saw during training. But overall, we've been seeing some interesting inference results. So for example, we don't have any China ground truth, at least not at the granularity we have for other regions. And with the China report that we did, we found out that it's actually follows pretty closely with what the government reports. So it seems to be promising.
And so that government reporting, is that on a more aggregated level, and you can aggregate up your predictions and check that they look similar?
Yeah, exactly. So for example, they can report, for example, at the state level and on a less granular level as well. And then we can just aggregate all of our power plants for that state and compare the time series with what the government reports. And it has been kind of matching quite nicely.
Right. So have you done the experiment where you train just on the Australia and the US data, and then you try and predict the UK or European power plants?
That's an interesting approach. We've been mostly just training on all of the ground truth data we have. But it is for sure important to check how your model performs on different subsets. And we do this kind of cross validation of our models. So we can also check that it can generalize somewhat decently.
Great. Got a series of questions from Erin Boyle, who asks, is it correct to say that you don't have any near real-time estimates of the plants being on and off? You're limited by the timescale availability of the satellite data. That was question A. And then question B was, how do the model predictions compare to self-reported emissions data from those companies where that's available?
Yeah, so those are good questions. I think the first one is, we are limited by satellites. But first of all, we have to consider here that we already have basically daily data from satellites. So for example, PlanetScope, as I shown, has basically daily images of each part of the world. And this will carry on getting better. I saw that Planet Labs is releasing a new satellite constellation that can take up to 30 images of each place of the world every day. So that's pretty nice. And then we also have this convenient factor that, for example, for coal power plants, they take a long time to turn on and off. So usually if they are on at a specific point of the day, it usually means they are on for the rest of the day as well. So that helps us with our models. And then for the second question, yeah, like I was saying, we can even compare with some other regions that have less granular emissions data or less granular power generations data, like China. And we have been seeing that the time series that we generate from our models do follow along similar patterns as the data that governments report.
Awesome. I had another question which popped up during the talk, which was, you mentioned the annotators, and I'm curious whether you are using an external annotation service or you do all the annotation internally. What was your experience of setting up that workflow and ensuring high quality?
Yeah, we have external annotators. If I'm not mistaken, they collaborate with us through the Global Energy Monitor data provider that I mentioned. And yes, it's been an interesting process. We go through these steps of onboarding them and training them for the tasks we need help with. And then they can do things like work on these Google spreadsheets that we set up for intuitive use from any annotator. And then we can then integrate them into our Postgres databases and eventually the data releases that we'll use for the models.
Gotcha. So these are truly volunteer annotators. Is that right?
Yeah, I think so. Yeah.
Because there's kind of whole wonderful world of at least with paid annotators, how you design your annotation schemes such that there's some cross-validation between annotator, and how do you set the rewards and include like test tasks and that kind of thing.
Right.
But I guess that's not so much concern. And you mentioned the plants turning on and off. Can you give us a sense of what percentage of the time a coal power plant is on and what percentage of the time it's off, and whether that varies by country?
Yeah, that does depend on the region, and it depends on other factors such as the fuel type and the capacity of the power plant. So it is usual, for example, that a very large coal power plant will be on almost all the time. But we do see some changes, for example, beyond the fact that sometimes it can be on, but at a lesser degree. So with less power generation. And we see interesting examples such as during the COVID lockdowns, for example, when China has a more strict lockdown, even the large power plants usually have a dip in their power generation and can actually be down for some days. So yeah, you can see these kind of changes. And then, fortunately, we do have the progress of some coal power plants being shut down and retired. So you can also check that the models do see that happening.
Yeah, great. A final semi-question from Michael Johnson about whether the presentation will be available online. So all of the recordings will be published after this on YouTube. I don't know, Andre, whether you have plans to make your slides available as a PDF as well.
Yeah, I think I could do, yeah.
Yeah, great. So Michael, look out for the release on YouTube. Any closing thoughts, Andre? Anything you wanted to pick up on?
I think that's all. Just to really thank you for the opportunity to be here in the conference, and yeah, hope anyone who's listening that isn't yet involved in climate tech that gets inspired and motivated to do some work on this as well. We need everyone's help.
Absolutely. And where can people find you if they want to ask some questions? Is your email the best way to go?
Yeah, they can chat with this email and the phone number that I have here on display. And you can also find me in the usual social media.
Brilliant. Thanks so much, Andre.